Section 23.5 deals with electric generators. As we've described earlier, an electric generator is a device in which some mechanical process causes a shaft to rotate. Attached to that shaft is a coil of wire, and that coil of wire is sitting in a magnetic field. So as the coil of wire rotates, the flux through that coil of wire is changing, and that will induce an EMF, cause current to flow. That's how we take a mechanical process and produce electricity with it. So let's take a look at a particular orientation. So here is a coil of wire that's rotating in a magnetic field. This is a top-down view of that coil of wire. And so this wire is rotating in a counterclockwise orientation. And so each leg of the wire, the leg on this side and the leg on this side, are represented by this point and this point. As this loop of wire rotates in a counterclockwise direction, this particular wire is moving with a velocity v in this direction. Remember earlier we derived the relationship that the EMF was equal to BLV, but the requirement was that all of these be perpendicular to each other, particularly that the velocity and the magnetic field be perpendicular to each other. So if I look at this, in this particular case, the velocity is not perpendicular to the magnetic field, but I can break the velocity up into components which are perpendicular and parallel to the magnetic field. So there's a perpendicular velocity and a parallel velocity. The perpendicular velocity will contribute to the induced EMF, whereas the parallel velocity will not. And so the perpendicular velocity, if I look at the construction here, this is theta, which means this is theta. And so the perpendicular velocity, this guy right here, is going to be v sine theta. That's v perpendicular. And so the EMF then is BLV sine theta, because the velocity, it's the perpendicular velocity that creates the induced EMF. Now, if we take this relationship and we remember what we've learned in Physics 111 with rotational motion, remember that with things rotating, I have an angular velocity omega, which is the change in angle with respect to time, and the linear or translational velocity of a particular point on a rotating object is going to be r times omega, where r is the radius or the distance from the center of rotation. So in this case, the r is this distance, which is w over 2. That's the distance from the center of rotation out to one of these legs of the wire. The whole dimension of the top wire is, or the whole length of the top wire is w. So now if I take that relationship and plug it into Faraday's law, EMF is going to be minus b times L. The velocity then is r times omega, so r is w over 2 times omega. You have to be careful to remember what's a w and what's an omega, times the sine of theta. Now w times L is just the area of the loop. So this is just minus b times a over 2 times omega sine theta. Now that's for one leg of that loop. Since we have two legs, again, there's a leg here and a leg here, the total EMF for one loop, one complete loop, is just twice this value. And if I have more than one loop, say I have n loops, then each one of them will produce a voltage, and so this will just be n times BA omega sine theta. And remember, because it's rotating, theta, if I take this equation and rearrange it, theta is just omega times time. And so this equation I can rewrite as NAB omega sine of omega t. And that relationship right there tells me what the EMF is as a function of time. So as this rotates, then the EMF executes a sine wave. And omega, remember your rotational dynamics, omega is 2 pi times the frequency, and frequency and period are inverses of each other. Period is 2 pi over omega. Period is the time it takes to go through one complete revolution. Because this is a sine wave, I can write this as some amplitude times sine omega t, where the amplitude, or the peak value, is just the coefficient of the trig function. Now, this will produce a sine wave. There's another figure or diagram in your book which shows how you can get current to flow in only one direction by the use of brushes and half rings. So now the current is always flowing in one direction. It still varies with time, but it's always flowing in the same direction in this circuit. Let's take a look at an example. We have a 400 turn loop inside a generator, and it has dimensions of 15 centimeters by 15 centimeters. It's a set of square loops. The magnetic field is half a Tesla, and the question is, at what rotational speed in units of RPM, revolutions per minute or rotations per minute, must a generator be rotating to produce a peak voltage of 50 volts? Well, the peak voltage is just NAB omega. In this question, they want me to find the rotational speed, so I want to solve for omega. So omega is just the peak voltage over NAB. So peak voltage of 50 volts, 400 turns. Area, it's a square loop, so it's 15 centimeters or 0.15 meters by 0.15 meters times the magnetic field of half a Tesla. And if I plug all those in, I get 11.11111 radians per second. Now the problem asked me to find it in revolutions per minute or rotations per minute, RPM. So 11.1 radians per second. Just do a little dimensional analysis. I want to turn radians into revolutions. So radians, revolutions, and I have in one revolution, I have 2 pi radians, and I want to turn seconds into minutes. So seconds, minutes. 1 minute is 60 seconds. So multiply all this out, and you get 106 RPM.